A star you watched last night could be gone forever by morning. These vanishing stars are not science fiction, but a genuine cosmic crisis, leaving astronomers with empty patches of sky where brilliant suns once blazed. We are exploring 30 celestial objects that disappeared without a single explanation. A journey that will fundamentally change how you see our universe. You will discover why the most stable things we know can simply cease to exist, challenging everything we think we know about space and time. We will uncover ancient supernova that left no trace and investigate modern telescopes finding ghosts in their data. What does it truly mean for reality itself when a star, the bedrock of the cosmos, can just flicker out of existence? One of the most profound disappearances in history was written in the sky over 1,000 years ago. In the year 1086, Chinese and Arab astronomers looked up and saw a new guest star, a point of light so brilliant it rivaled the planet Venus, and was visible even during the day. For months it shone, a spectacular supernova, and then it slowly faded from view. According to everything we know about stellar deaths, that cataclysm should have left a permanent mark. A supernova remnant, a vast and beautiful cloud of glowing gas, should still be there, expanding slowly for all eternity. Or at the very least, the dense, spinning core of the dead star, a pulsar, should be sending out regular beams of radiation. Yet when modern astronomers point the Hubble Space Telescope and the most powerful radio dishes at that exact patch of sky, they find nothing. It is simply empty. The star is gone, and it took all its cosmic debris with it. How is that possible? One compelling theory is that they witnessed a failed supernova. This is a star so massive that its own core collapse was too powerful. Instead of blowing its outer layers into space in a glorious explosion, the entire star simply imploded, falling directly into a black hole without a final, fiery farewell. The light those ancient scholars saw may have been the last gasp of a star being swallowed by the darkness it created. This idea turns stellar evolution on its head. We thought we understood the death of stars, that they went out with a bang, not a whimper. But this case suggests some stars might just give up. They vanish, leaving behind a silent black hole and a historical record that mocks our understanding. It forces us to question if we are even looking for the right things. Are the ghosts of dead stars hiding in the voids between the light, so dark and quiet we cannot see them at all? Just a few years ago, a star named V838 Monocerotis staged a performance that defied all known scripts. In January 2002, this previously faint star erupted, its brightness increasing by a factor of 1,000,000 in a matter of days. For a brief, spectacular moment, it became one of the brightest stars in our entire galaxy. But this was no ordinary nova. It did not blast its material away. Instead, it seemed to be engulfing itself in a rapidly expanding shell of gas, a cosmic light show with no clear cause. Then, as quickly as it flared, it faded back into profound obscurity. The star itself became incredibly difficult to observe, a faint whisper of its former brilliant self. What happened in that core? The leading theory is a stellar merger, a violent dance where two stars collided and became one. The immense energy released would explain the sudden, incredible flash. Another possibility is that we witnessed a completely new class of eruptive star, an engine of destruction we do not yet have a name for. The true ghost of this event, however, lies in its light echo. As the initial flash of light expanded outward, it illuminated vast, ancient dust clouds surrounding the star. This created a stunning, ethereal halo that grew for years, a cosmic fossil of that single, violent moment. We were not looking at the star itself, but at its ghostly fingerprint, a memory of the event etched onto the sky. So is the star of V838 Monocerotis still there, hiding in a dim, changed state? Or did that single outburst fundamentally transform it into something else entirely? A stellar corpse we can no longer recognize. This single observation forces us to rewrite the textbooks on stellar behavior. It proves that the lives of stars are not always slow, predictable burns, but can be punctuated by sudden, violent, and mysterious chapters. These glass plates from a century ago are more than just historical artifacts. They are time machines. Long before digital sensors, astronomers would coat these plates with light-sensitive emulsion and expose them for hours inside giant telescopes, etching the night sky onto glass. For decades, these fragile archives gathered dust, their full secrets locked away until modern technology could read them. Now, through painstaking digitization, we are comparing these century-old portraits of the cosmos with today's digital sky surveys, and we are finding that some of the stars have simply stepped out of the picture. One specific case involves a star clearly recorded at a moderate brightness on multiple plates taken between 1910 and 1950. It was a fixed point in the constellation, another anonymous sun among millions. But when powerful automated telescopes scanned the same precise coordinates decades later, that point of light was gone. It had vanished without any trace. So what happened? The first and most logical suspicion is a data error. Perhaps a tiny flaw in the old emulsion was misinterpreted as a star. Maybe it was not a star at all, but a transient event, like a distant asteroid that just happened to be passing through the frame during that long exposure, mimicking a fixed star. Yet the star appeared on multiple plates over many years, which makes these simple explanations feel unsatisfying. This historical detective work reveals a profound truth about the universe. The very act of looking back at these old records forces us to question the reliability of our own data and the assumed permanence of the heavens. If a star can be present for 40 years and then disappear, what does that say about the stability of the cosmos we think we know? This theme of vanishing acts does not end with these dusty plates. It only grows more urgent with our modern, all-seeing digital eyes. The European Space Agency's Gaia mission is building the most precise three-dimensional map of our galaxy ever attempted, a monumental digital atlas of nearly 2 billion stars. Yet within this ocean of data, astronomers are fishing for ghosts. They have flagged stars that, between one data release and the next, appear to have moved in impossible ways or vanished from their expected positions entirely. This is the realm of astrometry, the ancient and precise science of measuring the positions and motions of celestial objects. A star disappearing in brightness is one thing, but a star disappearing from its own coordinates is something else entirely. It is like a person's photograph fading from a family portrait, compared to the person's entire chair being suddenly, inexplicably empty. The first instinct is to question the instrument. Could a cosmic ray have struck Gaia's sensitive detector, creating a false signal? Perhaps these are stars with extraordinarily high proper motion, moving across the sky so quickly that they simply drifted out of the search area between observations. Each candidate requires painstaking verification, a process of elimination in a dataset of unimaginable scale. The sheer number of stars Gaia observes makes a few statistical flukes almost inevitable, but it is the outliers, the stubborn anomalies that refuse to be explained away, that hold the potential for discovery. This is where big data collides with cosmic mystery. Our most advanced mapping tool is not just filling in the blanks on our galactic chart. it is revealing new, fundamental questions written in the empty spaces. The search now expands beyond a single point of view, seeking answers from the full spectrum of light. The most baffling vanishings are the ones that occur across every channel of perception. An object might wink out invisible light, yet still broadcast its presence through the crackle of radio waves or the searing heat of X-rays. But what happens when every single one of these signals cuts off at once? This is the Multi-Wavelength Vanishing Act, and it represents a deeper, more final kind of silence. Consider a system known as an X-ray binary, a cosmic duo where a dense object like a neutron star or black hole slowly devours material from a companion star. As this stolen gas spirals inward, it heats to millions of degrees, unleashing a torrent of high-energy X-rays. For decades, a particular source might shine brightly in this violent light, a known and predictable beacon. Then, one day, it simply stops. The X-ray telescopes detect nothing. Radio observatories hear only silence. Even the infrared glow from the surrounding accretion disk, the very pipeline of material, seems to have evaporated. Every frequency goes dark simultaneously. How can something so active in so many ways just switch off? The most dramatic explanation is a total and sudden collapse. Perhaps the neutron star at the heart of the system, gorged on a final, critical meal of matter, passed the point of no return and imploded into a black hole. In this scenario, the collapse is so complete that it chokes off the very processes that made it visible, like a furnace whose door has been permanently sealed. Another possibility is the cessation of accretion itself. The stream of material from the donor star could have been abruptly disrupted, perhaps by a stellar flare or a gravitational interaction with a third, unseen body. Without a constant supply of fuel, the entire brilliant engine shuts down, leaving behind a cold, dark remnant. This all-frequency disappearance is so troubling to astrophysicists because it rules out the simpler, more local explanations. It cannot be a passing dust cloud which would only block certain wavelengths. It is not just a change in the object's orientation, which might hide one signal but reveal another. This is a fundamental change of state, a cosmic system undergoing a catastrophic and total rewrite of its own rules. It forces us to stop looking at the sky through a single lens and instead listen with every instrument we have, because the final clue to a star's disappearance may not be in the light we see, but in the silence that follows across the entire spectrum. A star's heartbeat is one of the most reliable rhythms in the cosmos. For decades, astronomers have tracked entire classes of variable stars, stars that pulse with the steady regularity of a cosmic metronome. Cepheids variables, for instance, brighten and dim over periods of days, their pulse rate so tightly linked to their true brightness that they became the very yardsticks with which we measured the universe. Then there are the Mera variables, aging red giants that swing through much larger changes in brightness over nearly a year, like a slow, deep breath. Their cycles are so predictable you could almost set your calendar by their rise and fall. But what happens when that rhythm simply stops and the star fades away, never to return to its former glory? This is the quiet, creeping enigma of the fading variable star. One particular star, monitored by both dedicated amateurs and professional observatories for over half a century, told a consistent story. Its light curve, a graph of its brightness over time, showed a beautiful, repeating wave. Year after year, it followed the same path, a dependable performer in the celestial orchestra. Then the variations began to weaken. The peaks of its brightness grew lower, the valleys grew shallower until the rhythm ceased entirely. The star did not explode, it did not vanish in an instant. Instead, its light simply dwindled like a fading ember until it slipped below the threshold of detection. it was a slow, quiet departure from the stage. Theorists are left with a handful of haunting possibilities. One is the concept of a final helium flash in a truly ancient star. In this scenario, a star in its final death throes might experience one last, unstable burst of nuclear fusion in its outer layers. This violent shudder could permanently disrupt the delicate internal balance that drove its pulsations, causing it to settle into a new, much dimmer state. Another explanation points not to the star itself, but to its immediate environment. Perhaps the star's pulsations were never the main source of its changing brightness. Instead, it might have been shrouded by a vast, orbiting cloud of dust and gas. As the cloud itself shifted and changed, it would reflect the star's light in complex ways, creating the illusion of a rhythmic pulse. The star's true fade, then, could simply be the final dissipation of that cloud, revealing the steady, faint light that was always there. This kind of discovery is only possible through the patient, long-term dedication of astronomers who watch the sky not for days but for generations. It is a different kind of mystery, not a sudden bang but a long, slow whisper. This gradual fade into nothingness stands in stark contrast to the violent, immediate vanishings that lurk in the most chaotic regions of our galaxy. This is the vanishing that defies all gradual explanation. One moment a star is there, a steady point of light in the telescope's gaze. The next time we look, that specific point in the cosmos has been switched off. This is not a slow fade or a rhythmic pulse growing weak. It is an instantaneous blackout, as if a cosmic hand simply reached out and snuffed a sun. The energy required for such an event is almost incomprehensible. A normal supernova, for all its violence, is a process. It takes time for the shockwave to tear through the star's outer layers, creating a brilliant, expanding fireball that can shine for weeks. But in these sudden blackout cases, there is no expanding shell of gas, no lingering afterglow, no supernova signal at all. The star was present, and then it was absent, full stop. The silence is the evidence. The most compelling and frankly unsettling hypothesis is that we are witnessing a star skipping its own funeral. This is the direct collapse, where a truly massive star reaches the end of its life, and its core gives up the fight against gravity in a single, catastrophic instant. Instead of rebounding in a titanic explosion, the entire structure simply implodes, falling inward directly into a newborn black hole. The outer layers of the star, with nothing to support them, follow suit, getting swallowed by the emerging darkness without so much as a final flash. It is a stellar death that happens behind a one-way curtain of gravity, leaving no trace for us to observe. This phenomenon was predicted by theory for decades, but confirming it meant catching a star in the very act of self-erasure, a needle in a cosmic haystack. That search is now the driving force behind time-domain astronomy, a field dedicated to scanning the sky over and over, night after night, hunting for anything that changes, blinks, or disappears. Every sudden blackout recorded is a potential data point for this most extreme stellar fate. It forces us to confront a haunting possibility. If stars can end this way, silently and without warning, how many of these cosmic ghosts are already out there, their passing marked only by an empty patch of sky where a sun once burned? The galactic core is a cosmic maelstrom where the rules of physics are pushed to their absolute limit. Here, at the very heart of our Milky Way, a supermassive black hole named Sagittarius A star holds court, its immense gravity whipping thousands of stars into frenzied, high-speed orbits. It is a place of perpetual chaos, shrouded in thick clouds of cosmic dust that block almost all visible light. We can only peer into this storm using infrared eyes, which see the heat glowing through the obscuring veil. And it is here, in this most extreme of neighborhoods, that another type of vanishing act has left astronomers utterly confounded. A brilliant object, likely a young and massive star, was clearly identified in one infrared survey of the region. It was a fixed point of intense heat and light, a beacon in the tumultuous core. Yet when more powerful telescopes with far greater sensitivity later scanned the exact same coordinates, the object was gone. It had simply ceased to register. How could something so substantial just disappear from the most observed patch of sky in the galaxy? The extreme environment itself offers several terrifying possibilities. One is a fate known as tidal disruption. A star orbiting too close to Sagittarius, a star, could be stretched and pulled apart by the black hole's ferocious gravity, not in a single explosive event, but in a slow, agonizing unraveling. The star's material would be siphoned away, its light fading over time until nothing was left but a faint stream of gas spiraling into the void. Alternatively, the star might not have been destroyed at all, but rather evicted. Gravitational interactions in this dense stellar cluster can act like a cosmic slingshot, flinging a star outward at millions of miles per hour. These hypervelocity stars are shot out of the galaxy entirely, becoming lonely travelers in the intergalactic dark. The object we saw might simply have been flung from its home, moving so fast that it left our field of view between observations. There is another, equally plausible explanation. What if the object was never a stable star to begin with? The region around a supermassive black hole is filled with intense magnetic fields and searing hot accretion flows. We could have witnessed a colossal flare, a temporary flash of energy on the black hole's own doorstep that, for a short while, outshone every genuine star around it. When the flare subsided, the false star would vanish with it. This makes the galactic center a unique and brutal laboratory. The normal, predictable life cycles of stars are rewritten here by extreme gravity and relentless violence. A disappearance in this realm is not necessarily a death. It could be a transformation, an ejection, or simply a cosmic illusion. It forces us to wonder if some stars do not die, but are instead reborn into something else entirely, or cast out into the great nothing between the galaxies. Every so often, the universe plays a trick on us. The most diligent search for a vanished star can lead not to a cosmic corpse, but to a case of mistaken identity. Before we can declare a true disappearance, we must first rule out the celestial imposters. Consider the slow-moving asteroid. A century ago, a tiny speck of light recorded on a glass plate during a long exposure might have been mistaken for a faint, fixed star. But that speck was not a sun at all. It was a chunk of rock drifting through our own solar system, its motion so slight across the sky that it appeared stationary for the duration of that single night's observation. If an astronomer catalogued it as a star, its subsequent absence in modern surveys would not be a mystery but a simple correction. Then there is the fleeting magic of gravitational lensing. The gravity of a massive object like a foreground galaxy can warp the fabric of space-time, acting like a giant magnifying glass. It can temporarily bend and amplify the light from a much more distant star behind it, causing that faraway sun to dramatically brighten for weeks or months. From our perspective, it looks like a new star has appeared, and when the alignment shifts and the lensing effect ends, it seems to vanish just as suddenly. We did not witness a stellar death, but a cosmic illusion, a trick of light and gravity. Even our own technology can create ghosts. A glint from a tumbling satellite or a piece of space debris can create a brief, star-like point of light that was never there to begin with. This is why the process of verification is so rigorous. Astronomers must become cosmic detectives, cross-referencing multiple observations across different wavelengths and archives. They ask a series of critical questions. Was the object seen more than once and in the same exact spot? Does its recorded color or spectrum match that of a real star? Can its position be linked to any known solar system object? This painstaking work is the foundation of good science, a crucial reality check that separates a genuine anomaly from an observational artifact. In an era where our near-Earth space is increasingly crowded with human-made objects, this task has never been more difficult or more important. It teaches us a vital lesson about the search for cosmic truth. The most extraordinary claims require not just a single observation, but an overwhelming weight of evidence. This disciplined skepticism is what allows us to confidently turn our attention to the remaining vanishings, the ones that stubbornly refuse every mundane explanation and point toward something far stranger lurking in the dark. Sometimes the simplest answer is the most beautiful. A star does not need to die to vanish from our view. It simply needs to put on a cosmic veil. Imagine a dense interstellar fog bank, a cloud of dust and gas so thick it can completely blot out a star's light for years, decades, or even centuries. This is the dust cloud obscuration hypothesis, a powerful reminder that the cosmos is a place in constant, flowing motion. Think of a car's headlights on a foggy night. The light is still burning brightly, but from your perspective, its brilliance is swallowed by the murk, reduced to a faint, diffuse glow. The same principle applies to stars. A young, volatile stellar object might experience a sudden, violent eruption, ejecting a vast shroud of dusty material that temporarily enshrouds it. Or the star itself could be on a long, slow orbit that carries it directly behind a previously unseen interstellar cloud. In both cases, the star plummets in brightness, seemingly disappearing from the visible sky. This is where our technology reveals the truth hidden from our eyes. Infrared telescopes are our window through the fog. Dust is excellent at blocking visible light, but it is far less effective at stopping longer infrared wavelengths, the energy we feel as heat. By switching to these infrared eyes, astronomers can often peer straight through the obscuring cloud and confirm the star is still there, shining warmly behind its temporary curtain. This explanation does not solve every mystery, of course. Some vanishings are too absolute, too final, but for many cases it provides an elegant and natural solution. It transforms a cosmic tragedy into a celestial performance, a reminder that the stage itself is alive with drifting dust and swirling gas. This idea of a dynamic, moving universe sets the stage for an even more direct form of disappearance, one where the star itself is not the actor that changes, but the entire theater moves around it. A star can also vanish by simply running away. This is the high-velocity escape, a stellar departure not into darkness, but into the deep. Some stars are not static fixtures, they are cosmic projectiles, flung from their homes at speeds exceeding 1,000,000 miles per hour. These gravitational slingshots occur in the crowded nurseries of star clusters or in unstable binary systems. When two stars in a tight binary encounter a third, more massive object, the complex dance of gravity can eject one of them at a tremendous velocity, casting it out on a solitary journey across the galaxy. For centuries, such motion would have been imperceptible, the star appearing fixed in its constellation. But with the precise astrometry of missions like Gaia, we can now see these runners in action. One compelling case involved a star that was clearly present in historical surveys but seemed to fade from its expected location in modern data. By meticulously comparing its position across decades, astronomers calculated a staggering proper motion. The star had not died, it was simply speeding away, its trajectory carrying it out of the original field of view and diminishing its apparent brightness as it receded. This kinetic explanation reframes absence. The sky is not a static painting, but a fluid, ever-changing map where stars are in constant, measurable motion. A blank spot on the chart may not mark a grave, but a highway, a path taken by a sun in flight. This realization that a star can physically relocate itself opens the door to an even more bizarre form of travel, one that does not rely on velocity alone, but on the very fabric of the cosmos. Einstein's theory of relativity tells us that space is not a rigid stage, but a flexible fabric warped by mass. This warping can bend the very path of light, creating one of the universe's most elegant illusions, gravitational lensing. Picture a colossal galaxy cluster drifting between us and a distant, faint star. The cluster's immense gravity acts like a giant, cosmic magnifying glass, curving the star's light around it and focusing that light toward Earth. For a brief period, that faraway star appears to brighten dramatically, as if it had suddenly ignited in a previously empty patch of sky. It looks, for all intents and purposes, like a new star has been born. But then, as the galaxy cluster continues its slow drift through the cosmos, the perfect alignment is lost. The magnifying glass moves away, the amplified starlight fades, and the star seems to vanish without a trace. We are not witnessing a stellar death, but the end of a perfect cosmic alignment. These phantom stars are celestial mirages, projections of light from a reality far beyond the apparent location. While astronomers today are adept at identifying most lensing events, what about a historical record? Consider a star noted by an observer a century ago on a photographic plate, a star that has never been seen since. Could it have been an exceptionally rare, short-lived lensing event, a flash in the pan that was captured only once and then lost to time? This possibility forces a profound shift in our search for vanished stars. The answer to the mystery may not lie in finding a stellar corpse, but in detecting the subtle, lingering warp in spacetime that created the ghost in the first place. To find a missing star, we must sometimes stop looking for an object and start looking for the bend in the universe's fabric that made it visible. Our understanding of stellar classification breaks down at this faint, forgotten borderland. Between the brilliant fires of true stars and the cold, dark worlds of gas giants lies a ghostly population of brown dwarfs. These are failed stars, objects born with too little mass to ignite the sustained nuclear fusion that powers suns like our own. They are cosmic embers glowing faintly with the residual heat of their formation, and then slowly cooling into near-total obscurity over billions of years. Spotting one is like trying to see a dying coal in a forest from 1,000 miles away. One deep infrared survey, scanning for the specific heat signature of these cold, dim objects, seemed to have found a promising candidate. The data showed a faint, warm pinpoint where no star was known to exist, a perfect match for a nearby brown dwarf. Yet when a newer, far more powerful telescope was aimed at that exact same spot, it found nothing but empty space. The candidate had vanished, so did the object disappear, or did we simply fail to see it correctly the first time? The extreme challenge of detecting brown dwarfs means that every observation pushes against the absolute limits of our technology. The initial detection could have been a subtle instrumental ghost, a statistical fluctuation in the data that mimicked a real object. But if the brown dwarf was truly there, its apparent disappearance is just as fascinating. These failed stars are not placid orbs, they are turbulent worlds with violent weather. A brown dwarf's atmosphere can be dominated by massive, swirling cloud decks made of molten iron and silicate minerals. A shift in this global weather pattern, a sudden clearing or thickening of these scalding clouds, could radically alter its brightness, causing it to drop below our detection threshold. Alternatively, the object itself might be cooling so rapidly as it ages that its heat signature simply faded away between our two observations. This mystery sits squarely in a poorly understood regime, a shadowy territory where the very definitions of a star and a planet blur into irrelevance. An object can easily slip in and out of our perception not because it has died, but because its nature is inherently fleeting and faint. If something as substantial as a failed star can flicker in and out of existence in our catalogues, what does that say about the countless darker, quieter objects we have not yet begun to imagine? The universe's greatest trick might be hiding its true mass in plain sight. What if some of these vanished stars were never stars at all, but something far older and darker? This is the dark star hypothesis, a journey into one of cosmology's most speculative frontiers. The idea centers on primordial black holes, hypothetical objects thought to have been forged in the intense furnace of the Big Bang itself. Unlike the stellar mass black holes created by collapsing stars, these would be ancient relics wandering the galaxy as cosmic ghosts from the very dawn of time. Their influence could explain some of the most puzzling disappearances we have recorded. Imagine one of these primordial black holes drifting silently through space on its endless journey. If its path carried it directly between Earth and a distant background star, its gravity would act as a tiny, perfect lens. For a few days or weeks, it would bend and focus the star's light, causing a brief, unexplained brightening, a microlensing event. To an astronomer, it would look like a star had suddenly flared and then faded back to normal. But if the primordial black hole were of a specific mass, its own faint, Hawking radiation or the glow of a hypothetical dark matter halo could theoretically make it appear as a faint, stable point of light for a short period. Its subsequent disappearance from our surveys would not be a death but a departure, the object simply continuing on its lonely orbit, leaving behind a mystery. While no primordial black hole has ever been conclusively confirmed, their potential implications are staggering. They are a leading candidate for the universe's missing dark matter, that invisible glue that holds galaxies together. This connection is profound. It means that the search for a single vanished point of light is not just about solving a stellar mystery. It is a direct hunt for the hidden architecture of the cosmos itself. A single, verified primordial black hole would revolutionize our understanding of everything, from the first moments of creation to the ultimate fate of the universe. The empty spaces on our star charts could be filled not with nothing, but with the silent, moving mass of the cosmos's oldest ghosts. The true architecture of our galaxy is written in invisible ink. The stars we see are merely the luminous highlights in a far grander and darker structure, one dominated by the gravitational pull of dark matter. This mysterious substance, which does not emit, absorb, or reflect any light, makes up the vast majority of the galaxy's mass. Its ghostly presence is felt everywhere, shaping the very rotation of the Milky Way and holding the entire cosmic structure together. While dark matter itself cannot make a star vanish in a flash of light, its silent, pervasive gravity could be the unseen hand that orchestrates some of the most perplexing stellar departures. Imagine a dense, wandering knot of dark matter, a phantom iceberg drifting through the sea of space. If such a clump were to pass through a tightly bound star cluster, its immense but invisible gravitational tug could act like a cosmic cue ball, scattering the stellar members. The orbits of these stars would be subtly or dramatically perturbed. Some could be flung onto new, unpredictable paths, making them appear to jump erratically in our sky surveys before fading into the background. Others could be ejected entirely, cast out of the galaxy as hypervelocity stars, their sudden absence from their home cluster recorded as a simple vanishing. This is an incredibly difficult mechanism to prove. How do you find the footprint of something that casts no shadow? You look for the holes it leaves behind. Astronomers might study a star cluster and find that its dynamics are inexplicably chaotic, with stars moving in ways that cannot be accounted for by the visible mass alone. The only logical culprit would be the gravitational influence of unseen dark matter, a passing ghost that stirred the pot and vanished without a trace. This idea forces a complete shift in our perspective. To understand why a star disappears, we may need to stop looking just at the star itself and start mapping the invisible landscape of dark matter that surrounds it. The fate of a sun may be sealed not by its own internal fires, but by a chance encounter with a fragment of the cosmos's deepest secret. This macro-scale dance of gravity and shadow stands in stark contrast to the next mystery, which unfolds in the bizarre and counterintuitive realm of the impossibly small. Deep within a star's core, the rules that govern our reality might not be absolute. There exists a speculative and deeply controversial idea that a star could vanish not through a collapse or a flight, but through a fundamental transformation, a quantum leap into a different state of being. This concept, known as quantum tunneling on a stellar scale, is not accepted science, but it stretches the imagination to its very limits. In the subatomic world, particles can perform the impossible, teleporting through energy barriers they classically shouldn't be able to cross. Now imagine that phenomenon scaled up to a cosmic level. What if, under pressures and temperatures we can barely conceive, the very heart of a star could tunnel through a quantum barrier? The result would not be an explosion, but a silent, instantaneous metamorphosis. The star's familiar nuclear furnace, powered by fusion, could suddenly transition into something entirely alien, like a vast lump of strange matter or a soup of free quarks. This new object would have radically different properties. It might be perfectly dark, absorbing all light that falls upon it, or it might emit radiation in a spectrum we are not equipped to detect. From our perspective, the star would simply cease to be, its light winking out as if a switch had been thrown. This idea is a testament to the power of unsolved mysteries. They force us to look beyond the textbooks and consider possibilities that sound more like science fiction. They remind us that our current laws of physics, as successful as they are, might only be a chapter in a much larger book. The potential for a star to undergo such a bizarre phase transition highlights just how much we still have to learn about the fabric of reality itself. While this remains a fringe theory, it underscores a crucial point in our search for answers. Before we can embrace such extraordinary ideas, we must first be absolutely certain we are not being fooled by something far more ordinary. Our star charts are built on trust, a fragile chain of data passed from one generation to the next. But sometimes that chain has a broken link. The 17th mystery forces us to confront a profoundly human truth, that the tools we use to map the heavens are just as fallible as the people who wield them. Consider the case of a star designated as Tycho 1723. For decades, it was a fixed point in a major catalogue, its position and brightness dutifully recorded. Yet when modern astronomers went to observe it, they found only empty sky. The investigation that followed was not a search for a black hole or a dark star, but a digital archaeology project. Researchers traced the entry back through layers of digitized records until they found the original handwritten observation log. There, in faded ink, was the clue. The astronomer had carefully noted the star's coordinates, but a subsequent transcriber, working late into the night, had made a single, crucial error. A 7 was misread as a 1, shifting the star's recorded position by a fraction of a degree, placing it in a patch of sky where no star actually existed. The vanished star was never there to begin with. It was a phantom born from a typo. This kind of error is not a relic of the past. Our modern, automated sky surveys face a similar challenge on an industrial scale. A single software glitch in a data processing pipeline can create thousands of false stellar detections. A cosmic ray strike on a telescope sensor can generate a perfect star-like signal that vanishes in the next exposure. These digital ghosts are then propagated into public catalogs, becoming real enough in our databases to be studied until someone notices the inconsistency. The monumental task of cleaning these catalogs, of cross-matching millions of entries to weed out the duplicates and the mistakes, is one of astronomy's most vital and unglamorous chores. It is a constant process of verification, a reminder that before we can chase cosmic mysteries, we must first sweep our own digital doorstep. This humble explanation is not a disappointment, but a cornerstone of good science. It is the necessary counterbalance that grounds our search for truth, ensuring that the anomalies we pursue are not merely the echoes of our own errors. Once we have accounted for every misplaced decimal and every software bug, the remaining vanishings shine all the brighter, their mystery undimmed by human fallibility. A star's own nursery can become its cage. Around many young stars swirl vast, pancake-shaped rings of gas and dust, the raw material for building new worlds. These circumstellar disks are not smooth and serene. They are turbulent construction sites filled with swirling eddies, coalescing planetesimals, and immense clumps of primordial material. Within this dynamic chaos, a simple cosmic coincidence can occur. A dense knot of dust and rock, perhaps a protoplanet in its earliest stages, can drift directly into our line of sight. When it does, it acts like a celestial dimmer switch, eclipsing the central star not for hours but for years. The star does not die, it is merely hidden behind the very stuff that will one day form its planetary children. The most famous example of this is Boyajian's star, a sun that baffled astronomers with its bizarre, irregular dimming patterns. Its light would dip by enormous amounts in ways that no ordinary planet could explain, suggesting a vast, complex swarm of orbiting debris was periodically blocking its light. Now imagine a much younger star, one still swaddled in a thick, opaque disk of material. If a truly massive clump within that disk, a giant vortex of dust or the core of a nascent gas giant, were to move into alignment, it could blot out the star completely. From our vantage point, the star would simply vanish, its light swallowed by the shadow of its own future. This mechanism beautifully connects stellar visibility to the very process of planetary birth. The empty patch of sky is not a grave, it is a womb, a sign of a solar system under active and violent construction. The star is still there, burning brightly, waiting for the cosmic dust to settle and reveal its light once more. This natural, astrophysical explanation grounds some of the most dramatic vanishings in a known process, yet it simultaneously opens the door to a far stranger possibility. If a natural disk can mimic a stellar disappearance so perfectly, what other cosmic architectures, perhaps built by intelligence far beyond our own, could achieve the same effect? The most provocative explanation for a vanishing star is not a force of nature, but a work of intelligence. The Technosignature Hypothesis dares to ask if a star's erratic dimming or sudden absence could be the signature of an advanced civilization. This idea, popularized by the bizarre behavior of Boyajian's star, suggests we might be witnessing something artificial, like a Dyson swarm. Imagine a vast, rotating network of solar collectors built by a species to harness the total energy output of its sun. Such a megastructure would periodically block the star's light in irregular, unnatural ways, creating a light curve unlike anything produced by planets or dust. For astronomers, this is the explanation of absolute last resort. a fascinating but extreme possibility that is only considered after every conceivable natural cause has been exhausted. Yet its very existence has transformed a small corner of astronomy. The search for technosignatures is now a legitimate field of study, a quiet but persistent effort to scan the heavens for patterns that defy natural explanation. A truly inexplicable vanishing, one that stubbornly resists all conventional models, becomes a prime candidate for this kind of investigation. It forces upon us a profound and haunting question. Are we alone in this vast cosmos, or could the ultimate fate of a star be not to die, but to be transformed into an engine for a civilization whose ambitions span millennia? This thought pushes at the very boundaries of our comprehension, a stark reminder that the universe might hold wonders we have not yet even begun to imagine. The final mystery, then, may not be written in the stars themselves, but in the silent, patient intelligence that could one day learn to command them. Our search for vanished stars inevitably runs into the hard limits of our own vision. Every telescope, from the smallest backyard instrument to the most colossal orbital observatory, has a fundamental detection threshold, a faintest possible magnitude of light it can reliably see. Think of it like trying to read a book in a darkening room. As the light fades, the words become harder to make out, until finally they cross a line and become invisible. The book is still there, the words unchanged, but your ability to perceive them has simply been exhausted. This is precisely what happens in our sky surveys. A star might be recorded as a faint, barely their speck of light in one survey, positioned right at the edge of that survey's sensitivity. Then, a decade later, a follow-up observation with a similar telescope fails to see it. We declare the star vanished, but the truth could be far more mundane. The star might have undergone a very slight intrinsic dimming, a routine stellar variation that was just enough to push it over the visibility cliff. Or its proper motion across the sky could have shifted its position by a tiny amount, moving it from a pixel where the detector was slightly more sensitive to one where it was slightly less so. In the noisy, statistical grain of the data, that minuscule shift is all it takes for a star to fall off our map. This is not a cosmic mystery, but a technological one. It reveals that our census of the heavens is not a perfect photograph, but a living document, constantly being revised as our tools improve. A star declared missing by one generation of telescopes might be effortlessly rediscovered by the next, its light patiently waiting for a sensitive enough eye to find it again. This perspective forces unnecessary humility upon the entire search. The universe we see is always a partnership between what is actually out there and the technological window through which we are looking. The emptiness we find might not be a void in space, but a limit of our own perception, a temporary silence waiting for a better ear to listen. Centuries before the first telescope, human eyes were the most sensitive detectors in the world. The royal astronomers of ancient China, the meticulous scribes of Babylon, and the time-keeping priests of the Maya spent their lives watching the sky, recording every anomaly with a precision that still astounds us today. Their clay tablets and silk scrolls are not just history, they are data. When a Chinese court astronomer in the year 154 noted a guest star appearing in the asterism they called Nanmen, they were logging a cosmic event of potentially immense importance. That faint point of light, visible for months before fading away, is a prime candidate for a true vanishing. If we could pinpoint its location today and find only empty space, the implications would be staggering. But unlocking these ancient secrets is a monumental task in itself. The first great challenge is translation. The ancient term for a guest star could mean a comet, a nova, a supernova, or even a particularly bright planet. Scholars must dissect poetic and symbolic language to extract cold, hard astronomical facts. Then they must account for the atmosphere of the past. A dust-filled sky from a recent volcanic eruption could have made a moderately bright star appear as a brilliant beacon, or a night of exceptional clarity could have revealed a faint object that was normally invisible. Precise dating is another labyrinth, requiring the correlation of imperial rain cycles and lunar phases with our modern Gregorian calendar. Yet for all these difficulties, the reward is a scientific treasure beyond price. These pre-telescopic records give us a long-term baseline that no modern instrument can ever replicate. They stretch our timeline of cosmic observation from mere centuries to millennia. A star that was present 2,000 years ago and is confirmed missing today would represent a phenomenon of incredible rarity and longevity, a slow cosmic death or transformation that plays out on a timescale far beyond a human lifetime. This connection between ancient wisdom and modern science adds a profound depth to our search. It reminds us that the mystery of the changing heavens is not a new puzzle for our digital age, but a question as old as civilization itself, written in the stars and on the tablets of those who first dared to understand them. Our own galaxy is not a fixed island in the void, but a ship sailing on a dark cosmic river. The entire Milky Way, along with our local cluster of galaxies, is being pulled relentlessly toward a mysterious point in space known as the Great Attractor. This is a gravitational focal point of unimaginable mass, a hidden heart of darkness in the intergalactic deep that commands the motion of millions of galaxies. On the scale of a single human lifetime, or even the entire history of astronomy, its pull on an individual star is so infinitesimally small as to be meaningless. Yet over tens of millions of years, this grand, universal current adds a tiny, persistent vector to the motion of every single sun in our galaxy. The star you charted in one position is ever so slowly being carried along by this flow. It is a reminder that our entire local frame of reference is in motion. We are not observing the heavens from a stationary platform, but from a life raft caught in a vast gravitational tide. This does not explain a star blinking out overnight, but it fundamentally reshapes our search. It means that a star's apparent position is not just a product of its own velocity, but also of our entire galaxy's journey through the cosmos. When we declare a star missing, we must ask if it has truly vanished, or if the entire coordinate grid we use to find it has subtly, imperceptibly shifted over deep time. This grand motion hints at an even more profound possibility. If the gravity of a hidden mass can pull entire galaxies, what else is it capable of? Could there be regions of space where the flow is so turbulent, the gravitational tide so fierce, that stars are not just moved but are entirely erased from view? The scale of cosmic vanishings expands beyond our galaxy to the very edges of the observable universe. Entire galaxies and the brilliant quasars at their hearts have staged their own, even more spectacular, disappearing acts. Quasars are the most luminous objects in existence, powered by supermassive black holes feasting on gargantuan amounts of gas. Their light can outshine 1,000 galaxies, a beacon visible across billions of light years. Yet astronomers have documented cases where these cosmic lighthouses have simply turned off. A quasar that shone brilliantly in one sky survey was, just a few years later, reduced to the faint glow of an ordinary galaxy in a follow-up observation. The supermassive black hole's engine had apparently shut down, its colossal appetite suddenly sated or its fuel supply abruptly cut off. The mechanism behind this is a feeding frenzy gone quiet. Vast clouds of gas and dust swirling in a doomed orbit can sometimes fall into the black hole all at once, creating a final, brilliant flare. Once that last meal is consumed, the black hole enters a period of quiescence, and the quasar vanishes from view, leaving behind a silent, dark giant. On a different scale, consider the fate of a dwarf galaxy. These small, faint collections of stars are often detected only as subtle overdensities in deep sky surveys. One might be clearly seen in one set of data, a smudge of 1,000,000 suns, only to be absent in a subsequent, even more sensitive survey. This disappearance is not a trick of the light, but a testament to the violent hierarchy of the cosmos. A dwarf galaxy orbiting a larger neighbor, like our own Milky Way, can be slowly, brutally torn apart by gravitational tides. Over hundreds of millions of years, its stars are stripped away and scattered into a faint cosmic haze, effectively erasing the galaxy from the celestial record. The timescales here are almost beyond human comprehension, but the principle is the same. We are witnessing catastrophic change, a fundamental rewriting of cosmic structure. This elevates the mystery of vanishing from a stellar curiosity to a universal process. The same forces that can snuff out a single star can also dismantle a galaxy of billions, reminding us that nothing in the universe, no matter how vast or brilliant, is truly permanent. A star's disappearance strikes a chord far deeper than simple scientific curiosity. It feels like a violation, a crack in the cosmic order we instinctively believe in. We are creatures born of a stable star on a planet with predictable cycles, and our minds are wired to seek patterns and permanence. The silent, sudden absence of a sun challenges that fundamental sense of security. This is the heart of the anthropic principle, the idea that our very existence as observers depends on a universe that is, for the most part, stable and lawful. We could not have evolved in a cosmos where stars flickered in and out of existence at random. So when we witness such an event, it feels profoundly unnatural because, from our limited biological perspective, it is. Our surprise is a measure of our own history. The technological power to scan the skies and notice these subtle absences is incredibly new. For almost all of human history, the fixed stars were a constant, a backdrop for our stories and our gods. That we can now detect their vanishings marks a pivotal moment, not just in astronomy, but in our relationship with the cosmos. We are no longer passive witnesses to a static tapestry. We are active detectives in a dynamic and sometimes chaotic theater. This quest to understand why stars disappear is therefore more than a collection of data. It is a deeply human endeavor. It connects our most advanced scientific tools to our most ancient psychological needs, the need for a universe that makes sense. Every empty patch of sky we find forces us to reconcile our desire for cosmic order with the unsettling, magnificent truth that we live in a universe capable of the impossible. We are not just decoding the mysteries of the stars, we are deciphering our own place within a story that is far stranger and more wonderful than we ever imagined. The static sky is an illusion, a snapshot in a grand cosmic film we are only now learning to watch. At the heart of this revolution is the Vera C. Rubin Observatory and its legacy survey of space and time, a project that will not just take pictures of the universe, but will capture it in motion. Night after night for an entire decade, its enormous eye will scan the entire visible sky, creating a time-lapse movie of the cosmos on a scale never before attempted. This is the dawn of time-domain astronomy, the study of how the universe changes over time. The sheer volume of data will be staggering, cataloging tens of billions of objects and detecting millions of changes every single night. This relentless surveillance is our best hope for catching a star in the very act of disappearance. Instead of finding an empty spot where a star used to be, we might witness its final moments, seeing the precise sequence of flickers and flares that precede its sudden blackout. That data would be a treasure trove, a cosmic black box recording the final seconds of a stellar life. It would tell us definitively if a star imploded into a black hole, was devoured by a dust cloud, or underwent some transformation we have not yet named. The survey will undoubtedly discover entirely new classes of vanishings, events so rare and fleeting that they have slipped through our observational nets until now. We might find stars that dim and brighten in patterns that defy physics, or objects that appear from nowhere and vanish just as quickly. This is not just about filling in the gaps on our star charts, it is about writing a whole new chapter in the book of stellar evolution. The next 10 years promise to tear down our image of a fixed, eternal heaven and replace it with a dynamic, living universe, a place where the only constant is change itself. A single professional astronomer, no matter how brilliant, cannot possibly sift through the tidal wave of data pouring from our modern observatories. This is where the global community of amateur astronomers and citizen scientists becomes an indispensable force, a network of millions of sharp eyes scanning the cosmos from their homes. Platforms like Zooniverse harness this collective power, inviting the public to inspect real astronomical images and data. The human brain possesses an unparalleled talent for pattern recognition, often spotting subtle anomalies and oddities that a pre-programmed computer algorithm might dismiss as noise or an error. The most famous testament to this power is the discovery of Boyajian's star. Professional astronomers had its bizarre light curve in their data for years, but it was a group of volunteers on the Planet Hunters project who first flagged it as truly strange, setting in motion one of the biggest modern mysteries in astronomy. That one observation, made by a curious person at their computer, fundamentally altered the course of scientific inquiry. This collaborative model does more than just process information. It democratizes the very act of discovery. For every researcher with a PhD, there are thousands of passionate amateurs with high-quality telescopes in their backyards and a deep, abiding love for the night sky. They are the first line of defense, the ones who notice when a familiar star flickers or a new point of light appears where none should be. Their contributions transform science from an elite pursuit into a shared human endeavor, a global project where anyone with curiosity can help write the next chapter in our understanding of the universe. This vast, distributed network of observers is our greatest asset in this puzzle, proving that the search for cosmic truth is not confined to mountaintop observatories, but lives in the collective wonder of everyone who has ever looked up at the stars and asked, "What is that?" These silent vanishings do more than puzzle astronomers. They unsettle something deep within us. We are born from starlight, living on a planet warmed by a predictable sun, and our entire history is built on the assumption of a stable cosmos. The fixed stars were the backdrop for our myths, our calendars, our voyages. To discover that this bedrock can simply crumble is to feel the universe itself shift under our feet. This cosmic uncertainty can provoke a genuine primal anxiety, a sense that the rules we rely on are not as solid as we believed, yet this very same feeling is also the birthplace of wonder. The realization that we do not have all the answers, that the cosmos is still wild and mysterious, is what ignites our curiosity and fuels our desire to look deeper. It is the same spark that drove the first humans to chart the planets and now pushes us to build telescopes that can peer back to the dawn of time. This journey teaches us a necessary humility. The universe is not a problem to be solved, but a vast, living narrative that we are only just beginning to read. To stand before its mysteries without a ready answer is not a failure of science, but its very essence. It is an admission that there is still more to discover, more to learn, more to wonder at. This acceptance of the unknown is the engine of all exploration, a force that has propelled humanity from ancient seafarers to modern astronauts. To embrace the mystery of a vanished star is to participate in the oldest and most human of quests, the search for meaning in the great, beautiful, and inexplicable dark. This search for cosmic ghosts does more than expand our knowledge. It builds the tools for our future. The relentless drive to measure the faintest flicker of a distant star has pushed the limits of precision photometry, the science of measuring light intensity. The same exquisitely sensitive detectors and software that scan the heavens for a vanishing sun are now being adapted to track the countless human-made satellites crowding our near-Earth space. This is not a coincidence, it is a direct technological transfer. The algorithms that sift through terabytes of telescope data to find one anomalous star are now helping to untangle complex problems in medical imaging, spotting subtle patterns in MRI scans or X-rays that might indicate the earliest signs of disease. The machine learning models trained on the cosmos are learning to find needles in haystacks here on Earth, from optimizing global supply chains to predicting financial market trends. This is the hidden engine of fundamental science. The goal was never to build a better satellite tracker, but in striving to understand the universe, we inevitably create the tools to better manage our own world. The connection runs even deeper than technology. Understanding why stars die, and especially why they might die suddenly and silently, is crucial for mapping the long-term habitability of our galactic neighborhood. We exist in a relatively quiet suburb of the Milky Way, but how stable is it really? By studying these catastrophic events, we can identify regions of the galaxy prone to violent gamma-ray bursts or supernova, cosmic disasters that could sterilize entire planetary systems. This knowledge allows us to assess the long-term safety of our own position in the cosmos and to understand the very conditions that allowed life to arise and persist on Earth. The economic return on studying a vanished star is not measured in quarterly profits, but in the profound and practical capabilities it gives our species. Investing in questions that seem to have no immediate application is paradoxically one of the most practical things we can do. It is an investment in the unanticipated breakthroughs that will define the next century, proving that the path to tangible progress often begins with the most abstract and beautiful curiosities. A single, verified signal from an intelligence beyond Earth would shatter our cosmic solitude forever. The vanishing of a star, if it were ever proven to be artificial, would instantly transform from a scientific curiosity into the most profound event in human history. How would our global civilization react to such a discovery? The immediate challenge would be one of verification and restraint. Protocols do exist, albeit in nascent forms, established by organizations like the International Academy of Astronautics. Their post-detection guidelines are a fragile framework for global cooperation, urging confirmation, transparent data sharing, and a cautious international consultation before any response is even considered. The first rule is to listen, not to shout. The immense distances involved create a natural buffer, forcing a slow and deliberate process, but the societal shockwave would be instantaneous. Think of the global internet, a system built for cat videos and commerce, suddenly grappling with the confirmation that we are not the only thinking beings in this vast dark. The potential for both wonder and panic is incalculable. This scenario forces us to confront our own immaturity as a species. Would we respond with unity, presenting a single, thoughtful voice for humanity? Or would we fracture with nations and corporations scrambling for advantage, turning a moment of cosmic connection into a new frontier for conflict? The ethical dimension extends to the star itself. If a Dyson swarm or some other megastructure is the cause, we are not just observing an engineering project, we are witnessing the transformation of an entire solar system, the ultimate act of a civilization securing its future. Do we have any right to interfere or even to make our presence known? The principle of planetary protection, long applied to our own solar system to prevent contaminating other worlds, would suddenly apply on a galactic scale. Our mere observation could be an intrusion. This thought experiment, while speculative, is a necessary mirror. It reflects our hopes for a cooperative future and our fears of our own destructive tendencies. It elevates the search for vanished stars from a data-driven hunt for cosmic phenomena to a philosophical preparation for a future we can scarcely imagine. The empty space where a sun once shone could one day hold not a corpse but a message, and we must ensure we are wise enough to understand what it means. So where do all these threads of cosmic mystery finally lead? The truth is that the vanishing of a star is not one single puzzle, but a vast spectrum of events, each with its own unique cause. Picture a great cosmic ladder of explanations. On the lowest, most common rungs, we find the simple answers, the celestial bookkeeping errors, and the passing dust clouds that temporarily hide a star from view. These are the cases solved by careful data cleaning and a second look through an infrared telescope. They are important not as disappointments, but as the foundation of scientific rigor, the necessary process of sweeping away the noise to reveal the true signal. Climbing higher, we reach the middle rungs, the realm of dramatic but natural astrophysics. Here reside the failed supernovas, the direct collapses into black holes, the stellar mergers, and the violent eruptions. These are the events that rewrite our textbooks, forcing us to accept that the universe operates on a scale of violence and finality we are only beginning to map. At the very top of this ladder, bathed in the light of pure speculation, are the most extraordinary possibilities, the paradigm-shifting ideas that challenge our very place in the cosmos. This is where we find the dark matter perturbations, the quantum phase transitions, and the hypothetical megastructures of advanced civilizations. These are not the first explanations we reach for, but they are the possibilities we must keep in mind, for they remind us that our current knowledge is a tiny island in a vast ocean of the unknown. The true power of this framework is its flexibility. It allows us to approach each new empty patch of sky without prejudice. The scientific process becomes a patient, methodical journey of moving each case from the mysterious to the understood, no matter where on that spectrum its final answer lies. We resist the temptation to force a favorite, spectacular theory onto every disappearance. Instead, we let the evidence, in all its forms, guide us to the appropriate rung on the ladder. This holistic view is our most powerful tool. It keeps our minds open, our questions sharp, and our sense of wonder intact, ensuring that the final chapter of this story is not a single revelation, but an endless, unfolding discovery. These 30 vanishings reveal a cosmos alive with change, a theater of constant drama far removed from the silent, static backdrop we once imagined. These empty spaces on our star charts are not failures of our science, but its greatest success, for they are the signposts pointing toward discoveries we have not yet made. They whisper of new laws of physics waiting to be written, of stellar life cycles more bizarre than our textbooks allow, and of possibilities that stretch the very definition of reality. Each disappearance is a lesson in humility, a reminder that our knowledge is a tiny island in an ocean of mystery. It is this endless frontier of the unknown that fuels the most human of all endeavors, our relentless curiosity. As our telescopes grow more powerful and our algorithms sharper, we will solve some of these puzzles, only to have the universe present us with new and deeper enigmas. The greatest discovery is not a single answer, but the perpetual invitation to look deeper and question further. If this journey to the edge of understanding has captivated you, please like this video and subscribe for more explorations into the cosmos's deepest secrets. Share your own thoughts on these celestial ghosts in the comments below. The next great mystery is waiting, and it will be discovered by those who dare to keep looking up.